Welcome you all. In this session, we are going to discuss Newton-Raphson method for power flow analysis. Outcome: after successful completion of the session, the student could able to analyze the power flow solution by using Newton-Raphson iteration method. Newton-Raphson method is mathematically superior to Gauss-Seidel method because of its convergence, fast convergence. For large systems, Newton-Raphson method is found to be more efficient and practical. The number of iteration records to obtain the solution is independent of the system size, but more functional elevations are required to each iterations. Newton-Raphson methods can followed with either polar coordinate version or in rectangular coordinate version, but polar coordinates version requires less number of equations, more reliability compared to rectangular coordinates. That's why usually we go for polar coordinates while you go for Newton-Raphson method to analyze the load flow. So here the flow chart for Newton-Raphson method to for load flow analysis is shown. So initially the input data are given. So from the input data, the bus admittance matrix is formed. So form the Y bus matrix. Then some assumptions are made. Assume that the initial value of Vi del I except the slack bus. Those assumptions are made. And first, let us take the iteration count as k is equal to 0. Then you are supposed to calculate the real and reactive power of that particular iteration. Find the bus whether the statcom is installed or not. So now again you need to calculate the p value. So now let us calculate the del p, del q, del pe and del f value. Check for convergence. If convergence is attained, then calculate the power flow and our result is displayed. If suppose convergence is not attained, then solve the equations of Jacobian matrix. So we know the Jacobian elements J1, J2, J3 and J4. Those elements need to be find out. Next, solve the main equation to attain the delta del, delta V, delta del S and delta Vs values. Update the voltage magnitude and phase angle and go for the next iteration. Initially we took the iteration value as k is equal to 0. We started with k is equal to 0. Now you need to update as plus 1, that is it becomes k is equal to 1 for the second iteration. Again the same process repeats until the convergence is attained. Once the convergence is attained, the result will be displayed. This is how the process goes on for Newton-Raphson method. So assuming a flat profile of 1 plus j0 for all bus except the slack bus is done. From Y bus matrix, convert the values of complex to polar form. So as I told, in polar form it is more convenient in case of Newton-Raphson method. So assume the value for convergence value and set the k value, that is the iteration value. Next you need to set the bus value. So depending upon the number of buses, the bus value will be checked up. So later on you need to calculate the value of p, then calculate the value of del p, del q, del pe, del f. You need to check for the convergence. If not, again you need to find the Jacobian elements j1, j2, j3, j4 and again the process goes on. So here the equations has been noted. So Pi minus Qi is equal to summation j is equal to 1 to n Vi Vj Vy Ij, and the angle is theta Ij minus del I plus del j. Similarly, Pi is equal to, so that is Pi minus Qi. Now here Pi is equal to summation j is equal to 1 to n, the same value, but here it is the cos of that value. And for that is real power, and reactive power is sine of this angle. So we'll be getting, so our general expression is del p del q is equal to j1 j2 j3. This is the Jacobian matrix, and the next column matrix is delta del and delta v. So del pik del qik is equal to, del pik is equal to pi minus pik. Similarly q value also. So this is how, by solving this you can find the solution for using Newton-Raphson method. So you need to calculate that del value, vi value. If the convergence value, you need to check for convergence. If it is s, you can stop, or else you need to go for the next iteration count by updating the iteration count value. Thank you.